In section 1, we talked about ions in solution, whether things were electrolytes or non-electrolytes, and we briefly talked about solubility and what made things soluble or not. What we're going to talk about in section 2 is the first type of reaction that takes place in and aqueous solutions. In chapter 3, we talked about double displacement reactions. We said that double displacement reactions are reactions that take place between two compounds and form two different compounds. And we said that they switch partners. The cations will switch places. And we sort of made some assumptions that those reactions would just occur. In reality, those reactions do not occur unless the ions are free to move. So if you take a solid and you put them together, no reaction is going to occur. The reactions must be put in solution for them to dissociate or dissolve for the ions to be free. Once they're in solution, those ions can mix. Sometimes a reaction will occur, sometimes they won't. So not all double displacement reactions that we learned to write in chapter 3 will occur the way we expected them to be written. All right, so a precipitation reaction is when you're going to take two of those soluble substances and you put them together, and the solutions, when they mix together, form an insoluble product. The new compound that's formed ends up as being insoluble, and therefore it settles to the bottom and forms a precipitate, we say. Now, we've heard the word precipitation in your lifetime used in the form of rain or snow or sleet. The word precipitation comes from a Latin precipa, meaning to fall out. Precipitation literally means to fall out of the sky. All right, so if we have precipitation falling, we have rain molecules or raindrops that build up and they fall from the sky. In a precipitation reaction, you have particles that are too heavy and they fall out of solution. Now, we talked about the word soluble. We said something that is soluble has different degrees of solubility. Substances can be soluble, slightly soluble, or insoluble. And as we said before in section 1, in order for something to be considered soluble, we say that the majority of the substance will dissolve in solution. In order for something to be slightly soluble, we say that probably at least 0.1 moles of the substance will dissolve in a liter of solution. So if at least 0.1 moles dissolves, just a little bit above it dissolves, we say it is slightly soluble. Things that are considered to be insoluble simply mean that less than 0.1 moles of substance will dissolve in 1 liter of solution. Now again, insoluble does not mean that no particles will dissolve. It simply means that most of the particles are insoluble. However, even the most insoluble compounds will have some soluble ions in solution. Now, how do we tell if something is soluble or not? We simply use our solubility rules. The solubility rules in your notes provided here are broken down as follows. These are something that you should work on memorizing just for the sake of use throughout. It doesn't have to be memorized, but it is something that you should work on for the sake of time. And for the chapter 4 test, at the end, you will not be allowed to use your solubility rules. You will need to know whether something is soluble or not. It looks complex, but in reality, there are only a few things that are considered to be soluble. So if you look at them and go memorize the things that are soluble and just know that everything else is insoluble. All their compounds are insoluble. Now, the first thing you should look at is the cation of a compound. If the cation is in group 1A, which is the alkali metals, all compounds that begin with an alkali metal are considered to be soluble. So if something begins with lithium, sodium, potassium, rubidium, cesium, it will be soluble. The same is true with ammonium. If something begins with ammonium, it will be soluble 100% of the time. So any compound, regardless what it is, if its first element is one of those 5 elements in group 1A or ammonium, it is soluble 100% of the time. Other than that, the rest of the things we look at are the anions. The following anions, again, are always soluble. Nitrates, NO3, bicarbonates, HCO3, and chlorates, ClO3, are considered to be soluble. Now, along with chlorates goes that whole family of perchlorate, chlorite, hypochlorite, all those as well are considered to be soluble. And the same is true with nitrates. Nitrites, NO2, negative, are generally soluble as well. So when you say nitrates or chlorates, it's the whole family. Now the halides, chlorine, bromine, and iodine, and fluoride for the most part too, are considered to be generally soluble. Most chlorides, bromides, halides, fluorides, whatever they are considered to be soluble. Only 3 exceptions. If they are with silver, mercury, or lead, then they are insoluble, but all other halides are soluble. Sulfates, again, are generally considered to be soluble. Most often, sulfates are soluble. Now, a few exceptions. Silver, mercury and lead are considered to be insoluble completely, whereas calcium, strontium, and barium sulfate are slightly soluble. For the most part, though, we consider those soluble, we could say. So focus on, again, silver, mercury, and lead. So if you look at Group 1A, my general guideline I suggest to students is you run through a checklist in your head and you're checking for solubility. You look at the first column periodic table. Is the cation of this compound in Group 1A? If the answer is no, we then say, is it ammonium? If the answer is no, we then move to the anion. If the anion is nitrate, chlorate, or bicarbonate, again, or any of those families of chlorates or nitrates, then again, it is soluble. So that's check 2. Check 3 is the second part, or the anion. If the answer is no to both those things, then we say, is the anion chloride, bromide, or iodide, or fluoride? If the answer is yes, it's probably soluble unless the first part is with silver, lead, or mercury. If the answer is no, we go into sulfate. If sulfate is the second part, again, generally speaking, it's going to be soluble except for silver, lead, or mercury. And we say that they are insoluble. If it's none of those, you've gone through all those checklists and it's still not one of those compounds, then you know the compound is insoluble. Now let's take a look at some practice problems here as what we do. These solubility rules will help us know whether something is going to be soluble in solution or form an aqueous solution, or whether it's going to stay as a solid in solution. That is very important when determining precipitation reactions. So if we look at these compounds, and again, look at your rules. I can't show them all on the screen at the same time, but you can look at your rules while I'm going over the examples. Silver sulfate, check 1. I look at the first part. Silver, is it Group 1A or ammonium? The answer is no. All right, so I go to check 2. Is the second part chlorate, nitrate, or bicarbonate? And I just realized I'm missing up here in this list acetate as well, C2H3O2 minus. Add that into your list as well. If it's none of those, then it is, move on to number 3. Is the second part a halide? No, it's not. So we move on to the final test. Is the second part sulfate? Yes, it is sulfate. However, is it one of these? It is. Therefore, we say it is insoluble. All right, so that is an insoluble compound. Let's go to the next example. Copper 2 sulfide. Copper 2 sulfide is CuS. Copper's plus 2, sulfide's S minus 2, so it's CuS. And silver sulfate was Ag2SO4. I skipped that part. Copper 2 sulfide, we look at the first element. Again, is it lithium, sodium, potassium, rubidium, cesium, or ammonium? No. Check number 2. Is the anion nitrate, bicarbonate, chlorate, or acetate? The answer again is no. So we go to check number 3. Is the anion a halide? The answer is no again. Remember, the halides are chlorine, fluorine, bromine, iodine underneath that family, the next to the last family on the periodic table. Is the anion a sulfate? No, it's sulfide. Sulfate, sulfide are different things. Therefore, we've gone through all the checklists. Because we've gone through the checklist of things that are soluble, again, we know this is insoluble. Let's go to calcium hydroxide. Calcium hydroxide, Ca is calcium. Hydroxide, and that's plus 2. Hydroxide is OH. It's minus 1, so it's Ca parentheses OH parentheses 2. A little practice for you there. So again, we look at it and we say, is calcium, lithium in first family, or ammonium? No. Is hydroxide one of the anions that we know are soluble, nitrate, bicarbonate, chlorate, or acetate? No. Is it a halide, which mostly are soluble? No. Is it sulfate? No. We've gone through the checklist again, therefore this is insoluble, which means it would form a solid in solution. So when I was putting a state symbol, that I put an S there. The next one, zinc nitrate, Zn is plus 2, NO3 is minus 1, so that would form Zn parentheses NO3 parentheses 2. First check, zinc, not in group 1A. Therefore, we move on to check 2. Nitrate. Nitrate is on the list, so automatically I know this is soluble, and I stop right there. Lead chloride. We're not given a number here, so we're going to assume it's lead plus 4. Remember what I said before, if you don't know a charge, you assume the most common one, so lead chloride is Pb plus 4 and Cl minus 1. So it's going to be PbCl4. From there, we simply look at the checklist again. Lead is not in that group of cations. Chloride is my halides down here, but lead is one of the exceptions. Lead 2 is one of the exceptions. Lead 4 is not. Lead 4 is not one of the exceptions, therefore it is soluble. And that's a tricky one because only lead 2 would be the insoluble halide. Sodium perchlorate. Na is plus 1, perchlorate is ClO4, that's negative 1, so it's NaClO4. Right away I look and I see sodium is part of the alkali metals, so this is automatically soluble. Now, once we can figure out whether something's soluble or insoluble or not, we are ready to start writing different types of equations for a precipitation reaction. Now, when you write a precipitation reaction, there are 3 types of equations we deal with. A molecular equation are the kind of equations we've been dealing with in Chapter 3. So when you learned how to write equations in Chapter 3 and all those equations you wrote, they were all molecular equations. An ionic equation is breaking apart the substances that are aqueous into their component ions. A net ionic equation is when you've canceled out all the soluble or unreactive ions, it is what is left after what are called the spectator ions have been crossed out. Spectator ions are the ions that are in solution that really don't react, and you'll see what I mean by that in our first example. In our first example, an aqueous solution of lead nitrate reacts with an aqueous solution of potassium iodide. Write molecular, ionic, and net ionic equations. First thing we do, we start with Pb, which is lead. It doesn't tell us which one, so we're going to assume that it's plus 4, lead nitrate. So Pb plus 4. NO3 is minus 1, so therefore it's Pb NO3 in parentheses 4. Actually, we're going to assume that's lead 2. I just had a typo there. It's supposed to be lead 2 in there. My fault. So it's lead 2 nitrate. Reacts with, and that's aqueous. So down here below, when we have something that's aqueous, put a symbol, a little state symbol in that, and a state symbol you've seen throughout the book is showing you what state of matter it's in. We put a little AQ down there. Reacts with potassium iodide. Potassium is K plus 1, iodide is I minus 1, so that's Ki. And then again, it said it was aqueous, we put an AQ with that. Now, the first thing we do is we have to predict our products. So since this is a double displacement reaction, we know lead is going to go with iodine, potassium is going to go with nitrate on the other side. So K is plus 1, nitrate's minus 1, it's going to form KNO3. Pb is plus 2, I is minus 1, it's going to form PbI2. Now the next thing we need to do to determine, first off, whether this reaction actually happens or not is what are the state symbols. So again, I need to go back and figure out if they're soluble or insoluble. Potassium nitrate. Potassium is in group 1A automatically, and nitrate also is in that list, so I know that is a soluble compound, and anything that's soluble I put an AQ with. Pb is not in my list of cations. Iodide is one of my halides, so I know most halides are insoluble, or sorry, are soluble. But lead 2 is an exception, so we know that is insoluble. So when it's insoluble, we put an S, and the S stands for solid. All right, so again, don't think of the S as soluble, it's solid. All right, so that is our molecular equation. We've written the molecular equation, and we learned, as we learned to do in Chapter 3, predicting products. Now we need to balance that equation as we've done in the past. When we balance the equation, I need to put a 2 here, and then I need to come back and put a 2 here. That's the molecular equation. The next thing we do to get an ionic equation is we take anything that is aqueous and we break them apart into their component ions. So, for example, lead nitrate is going to break apart into solution into Pb plus 2 ions that are aqueous and 2 nitrate ions in solution that are aqueous. So if I take a container and in that container of water, I put that in there, I'm going to have a Pb ion floating around and 2 little nitrate ions floating around for every molecule. That's what that's saying. Since I have 2 of this particle, it's going to break apart into 2 K plus ions that are aqueous, and 2 iodide minus ions that are aqueous. All right, so before the reaction, I have 2 containers. The first container is here, and I have Pb and NO3 floating around in it. And the second container is here. I have K and I floating around in there. The ions are dissolved or dissociated in water. They're free to mix. I dump them into a container, and this is now my container. All right, so I'm putting in the container. When I put them in the container, on the other side is what is happening. The K and the NO3 continue to float around in water. They stay in ion form. So I have 2 NO3s floating around still, and I have 2 K pluses floating around. But the Pb, I, and the I mix together in a 2-to-1 ratio to form something new, and they sink to the bottom of the container. They form a solid out of that. Solids, liquids, and gases, state symbols, when you're writing your ionic equation, you do not break apart. You leave them alone. All right, so this is the ionic equation, sometimes called a complete ionic equation. To move on to the net ionic equation, what we do is we cancel out in the ionic equation anything that is the same on both sides. So I have 2 nitrates in the reactant phase floating around, and they're still floating around in the product phase. They didn't do anything. They're just floating around watching the reaction. The only reason they're there is because they came with nitrate in the beginning. I have 2 K plus ions floating around before and after the reaction, so they aren't doing anything. We call those things spectator ions. So spectator ions in this case are K and NO3. Why are they called spectators? Well, if you think of the term spectator, what that is, a spectator is a person who just sits and watches. Those ions are doing nothing in this reaction. They are simply floating around in solution doing nothing. They are just sitting and watching. Now, the last reaction, we take what is left and we recombine things. So our net ionic equation is what is actually happening. And overall, this whole thing, what is actually taking place? So we have Pb plus 2 ions that are reacting with 2 I minus ions in solution. And as a result, they are forming PbI2 molecules that are settling out of solution. Now, when you write your net ionic equation for a precipitation reaction, it is important to understand the cation must come first, then the anion producing the product. And the easy way to remember that is on the reactant side, if they're not written this way, Pb first, I second, then you've written them wrong.